Welcome, Hornets. This is Mr. Lamb once again, and today we're going to be taking a look at a second edition of the difference quotient and working with limits. Specifically, what we're looking at in this is what happens with quadratic equations. In our previous video, we saw that the linear equations, tangent lines are simply the line, and therefore the slope of a tangent line is going to just be the slope of that line. So what are we going to see today? Well, today we're going to be taking a look at quadratics. So specifically, I want to work with the difference quotient for f of x equals 2x squared plus 1, and we're going to be putting it into our limit as delta x approaches 0 for f of x plus delta x minus f of x over delta x. We're going to be looking for a pattern, and then we'll do a couple, add a value, and try to see, do we see that happening, and can we validate that pattern? So let's go ahead and first figure out what is the f of x plus delta x. This is why I made you do the difference quotient the other day. It was absolutely imperative that you are able to do these without really having to think too much. So putting this together, we have our 2x squared plus 4x delta x plus our 2 delta x squared plus 1. Putting it into our limit statement now. And please be aware, I am modeling the process that you have to go through. You do have to put the limit statement in front every single step. Please don't forget that. If you do, you will lose all of the credit. It's a terrible way to lose the credit here when you've done all of the work and you know how to do it. So minus our f of x all over delta x. Now, we've done this before, so we know that as we add our like terms, the only terms that remain are terms with a delta x. See it? GCF is delta x, so the limit as delta x approaches 0 for delta x times 4x plus 2 delta x all over delta x, and the delta x reduces. You'll notice I now can apply my limit statement. The limit as delta x approaches 0, and we have a delta x, 4x plus 2 delta x. According to our rules of basic limits, we apply it, we plug it directly in, and we simplify, and we get an expression of 4x. I want you to look up at the original. Is there any way we can get a 4x from this? I want you to think about that. Let's do another quadratic. This time, we're going to put a linear behind it. So let's do f of x equals 3x squared plus 4x. Now, we know that the 4x is going to end up having a 4 at the end, so we've got a little bit that we can think about. After all, it is linear. And when we do the difference quotient with a linear, i.e. the slope of the tangent line of a linear equation, we're just talking about the slope of that line. That's 4. All right, let's find out what is f of x plus delta x now. That's 3x squared plus 6x delta x plus 3 delta x squared. And then we have this piece. So plus 4x plus 4 delta x. Woohoo! Now we're going to put it into our limit statement. The limit as delta x approaches 0, give yourself a lot of room because it's a big one. 3x squared plus 6x delta x plus 3 delta x squared plus our 4x plus 4 delta x. Then we're subtracting 3x squared, subtracting 4x, and it's all over delta x. 3x squareds cancel, 4x's cancel. Every term has a delta x. We factor it out. So we have delta x factored out, leaving us with 6x plus 3 delta x plus 4 all over delta x. Delta x is reduced. The limit as delta x approaches 0, it's now a basic limit. We can just plug in delta x equaling 0. When we do, 3 times 0 goes away, and we're left with 6x minus 4. So here's the 4 we got from the constant. We knew that was happening. But look at the 6x. What gives us 6x from our basic rule? It sure looks like that power is coming down into the front and multiplying by the 3, and the power is dropping by 1. Let's see if that works with another one. Let's do 4x squared. F of x equals 4x squared. Let's do plus 3x minus 2. Huh. Now that's interesting. When we had the 1 went away. Let's just see, where was it? Here it was. The 1 went away. See, it's gone. The constant disappeared. That's pretty cool. All right. Why would that be? What does a constant line look like? Let's just take a moment and think about that. What does a constant line look like? It's a horizontal line. We know that the slope of a line is the tangent, is the derivative. What's the slope of a horizontal line? It's 0. That's why the constants are going away. They're going to 0. The linear equations are going to the constants of that slope. And this appears to be that the power is moving down and multiplying by the coefficient. If that's easy, then if that's the case, we should be able to see our derivative as 8x plus 3. Let's see if we get that. F of x plus delta x. We have 4x squared plus 8x delta x. We're going to be adding to it 4 delta x squared. You'll notice I'm having to write small because it's huge. Plus 3x plus 3 delta x minus 2. The limit as delta x approaches 0. Let me put this whole thing in. 4x squared plus 8x delta x plus 4 delta x squared plus 3x plus 3 delta x minus 2 minus 4x squared minus 3x plus 2 all over delta x. The 4x squared cancels, the 3x goes away, the negative 2 goes away, and we're left with the limit. As delta x approaches 0, we factor out the common GCF of delta x, leaving us with 8x plus our 4 delta x plus 3 all over delta x. Look at what we got. The limit as delta x approaches 0 for 8x plus 4 delta x plus 3, and our answer is 8x plus 3. So, right here, the pattern held. All right, so we now can see several things. First of all, when we use the difference quotient, we get certain things. A constant goes to 0. A linear goes to a constant and is just the variable or the coefficient. And the quadratic drops to a linear. And there's a multiplication involved. Notice how each situation drops to the next level of degree. A constant has x to the 0 and then drops to x to the 0 with the 0 in front as a coefficient. A linear, which is x to the first, drops to x to the 0. A quadratic drops to a linear, so from x to the second down to x to the first. And we start to see our first pattern. Thank you very much, Hornets. Please be aware this is what we're going to be dealing with. You will be asked to use the difference quotient in order to find the expression for the instantaneous rate of change, and shortly I'll be showing you how to do it at a value. Thank you very much. Take care and be well.